Antigravity for aerospace applications. Antigravity effects can be implemented by manipulating spacetime. This paper reviews several different theoretical approaches for exploring the possibility of controlling gravity by generating forces that counteract, or otherwise modify, gravity for the purpose of aerospace propulsion. Einstein's general theory of relativity is the theoretical framework guiding this study. The paper also reviews other antigravity approaches via the interaction of quantum theory with gravitation. And it explores the question of which method or technique is best suited for aerospace applications and evaluates the make or break issues that limit them. Introduction. Gravity is the bane of aerospace transportation. The force of the Earth's gravitational field acts to pull all objects, whether in motion or at rest, downward towards the Earth's surface. Because aerospace transportation involves the motion of vehicles through the atmosphere and/or into space, propulsion engineers are always faced with the requirement that aerospace vehicles will have to carry enough propellant and associated tankage in order to provide enough propulsive thrust to overcome the downward pull of gravity and achieve rectilinear motion. Energy has to be expended by a propulsion system to overcome the force of gravity in addition to providing for rectilinear motion, and the majority of propulsive energy is dedicated to overcome gravity. The aerospace propulsion engineer is faced with two choices for the control of gravity in this regard: passive control and active control. Modern aerospace propulsion technology, which is based on accumulated scientific knowledge since recorded history, can only achieve the passive control of gravity, whereby a given propulsion device must develop a thrust that will passively counteract the Earth's gravitational pull, lift a vehicle off the surface, and propel it through the air or into space. Newton's laws of motion and gravity require that the fuel fraction of any aerospace vehicle can never be less than that given by a simple function of the ratio of the vehicle's maximum speed to the speed of its rocket plume, jet, fan, or propeller wake. For example, this limit implies that a single-stage rocket that accelerates to escape velocity must be composed of more than 93% fuel. That is because a rocket must accelerate its working fluid from rest, relative to the rocket, up to its exhaust speed. Thus, exhaust speeds for aircraft and chemical rockets are limited by material science, chemical reaction rates, and engineering factors to only a few thousand meters per second. To date, there is no technology that can achieve the active control of gravity. If one could eliminate or otherwise control the Earth's gravity field, then one has the ability to dramatically reduce the amount of propellant, its tankage, and the overall structural size and mass of an aircraft or rocket, because there will no longer be any need for these to overcome the pull of Earth's gravity while transporting a payload across the globe or into space. Instead, aerospace vehicles will only need to have the propellant mass and infrastructure necessary to change their kinetic energy from rest to a final velocity necessary to achieve atmospheric flight or space orbit. The Earth's gravitational well will no longer have any impact on aircraft, launch vehicle, or spaceflight dynamics if one were to achieve active gravity control. Aerospace vehicles would merely levitate in air and their propulsion systems would be optimized for change in velocity missions. However, it is possible to envision a form of active gravity control propulsion that would not require a change in kinetic energy. One of the primary concepts for the goal of affecting gravity is antigravity, which is a colloquial expression that specifically means the negation or repulsion of the force of gravity. A more general term that encompasses this notion and other possibilities is gravity control. If antigravity exists, it can be exploited to counteract or nullify the gravitational pull, or attraction, of a planetary, or stellar, body that acts upon a much smaller body. Einstein's general theory of relativity gives a prescription for a variety of different antigravity generators. Even Newton's law of gravity offers several different classical prescriptions. Newton's law of gravity can be used to simply nullify the gravity field of one body acting on another body by using a clever arrangement of masses. The theoretical possibility of antigravity also appears in quantum gravity theories, cosmological vacuum or dark energy, and quantum field theory. This report reviews all of these topics. The report will also review the topics of gravity control that include the production of antigravity, self-lifting, forces induced by quantum vacuum zero-point energy and by non-retarded quantum interatomic dispersion forces in a curved spacetime, that is, in a background gravitational field. The reader should bear in mind that many of these concepts are nowhere near having any form of practicable engineering implementation. However, The report will provide theoretical estimates to guide the way toward technological implementation of antigravity. Concepts for antigravity within Newtonian physics. The basic form of Newton's law of gravity is given by the standard expression for the gravitational force, F, that mutually acts between two masses. F grav equals, g m1 m2, r squared. Where the negative sign indicates that Phi is a mutual force of attraction, g is Newton's universal gravitation constant, 6.673 by 10 to 22 in m2 ik2, and m2 are two interacting masses, and r is the radial distance between the two masses. Note, mks units are used throughout. Observe in equation 1, that the force of gravity acting on a small test mass becomes stronger when the other, gravitating, mass is larger in magnitude or when the distance between them is very small, or both. Also recall that equation 1, and Newton's second law of motion, F equals Ina, to define the magnitude of the gravitational acceleration a2. That acts on a small test mass m due to a larger, gravitating, mass m. Ag equals gm, r squared. If Earth is chosen to be the larger gravitating mass so that m equals me, 5.972 by 1024 kilograms, then according to equation 2, a small test mass m placed near the Earth's surface, whereby Re, 6.378 by 106 meters, will experience a downward gravitational acceleration of a, g equals 9.81 meters per second squared. Negating Newtonian gravity. It is possible to design an anti-gravity machine that can nullify Earth's gravity field using Newton's law of gravity. One way to use equation 1, to nullify the Earth's gravitational pull at a particular location would be to locate another planet of equal mass above that location. The forces from the two Earth masses will cancel each other out over a broad region between them. Everything within this broad region will be in free fall. However, this is not a practical solution for aerospace flight since there is no way to manipulate and control another planetary-sized body. Along similar lines, Ford suggested to consider using a ball of ultra-dense compact matter, corresponding to dwarf star or neutron star matter, 10 inches to 1018 kilograms/m3, having a diameter of 32 centimeters and a mass of 4 million metric tons. This ultra-dense ball will have a surface gravitational, attractive, force of 1 gram. This small, ultra-dense ball could be placed near the surface of the Earth and its 1 gram gravity field will cancel the Earth's 1 gram gravity field. All test objects placed in the broad region between the small ultra-dense ball and the Earth will thus be in free fall. Another option Ford suggested would be to shape the compact ultra-dense matter into a disk that is 45 centimeters in diameter and 10 centimeters thick, and having the same mass and density as the small ultra-dense ball. Its gravitational acceleration is ag equals 4 GPR, where p is the mass density of the disk and t is its thickness. In this case, the disk will have a force of gravitational attraction that is the same on both sides, and it will be uniform near the center of the disk where the strength of the gravitational force will be 1 gram. If this disk were to be placed very close above the Earth's surface, then there will be a gravitational force of 2 gram above the disk, equals 1 gram due to the Earth's gravity field plus 1 gram due to the topside gravity field of the disk, while underneath the disk near its center there will be a gravity-free, or free fall, region because the Earth's gravity field underneath is cancelled by the gravity field of the disk's bottom side. While these are interesting anti-gravity machines, they are unfortunately not feasible from an engineering standpoint since one does not yet have the technology or means to create and handle ultra-dense compact matter. Energy estimate for Newtonian levitation. An ideal propulsion breakthrough could take the form of the anti-gravity-based levitation of an aerospace vehicle within the Earth's atmosphere. Rockets like the Air Force DC-SA can hover above the ground for a time that is limited by the amount of rocket fuel available. But an ideal anti-gravity propulsion device should allow for the indefinite levitation of a vehicle above the Earth's surface. It is illustrative to estimate the energy required to levitate a 1 kg test mass above the Earth's surface. This will help quantify a potentially key engineering parameter for such a levitation system. A generic estimate can be found by considering the amount of energy per unit mass required to nullify the magnitude of the Earth's gravitational potential energy era for a test mass and hovering at height h above the Earth's surface. E lev equals gm plus m, h. Equation 3, can also be derived by calculating how much energy is required to completely remove a test mass from the Earth's surface to infinity. This calculation is more in line with the analogy to nullify the effect of gravitational energy. And equation 3 also represents the energy required to stop a test mass at the levitation distance h if it were falling in from infinity with zero initial velocity. Setting h re and n equals 1 kg in equation 3, the result is C equals 62.5 megajoules/kg. This is 2.05 times the kinetic energy required to put the test mass into low Earth orbit, LEO. However, this estimate will require some adjustment that depends upon the type of theory and its technological implementation. That is because the operational energetics of a putative antigravity propulsion system must be considered in conjunction with ELEV. Concepts for antigravity within general relativity. In the sections that follow, the known types of antigravity that can be derived from Einstein's general theory of relativity are described and summarized, which is the modern relativistic theory of gravity. Antigravity via gravitomagnetic forces. Historical foundations. Heaviside, Einstein, prior to the 1916 publication of his general theory of relativity, Tearing, see also, reference 11, showed that general relativity theory provides a number of ways to generate non-Newtonian gravitational forces via the splitting of gravitation into electric and magnetic field type components. These forces can be used to counteract the Earth's gravitational field, thus acting as a form of antigravity. General relativity theory predicts that a moving source of mass energy can create forces on a test body which are similar to the usual centrifugal and Coriolis forces, although much smaller in magnitude. These forces create accelerations on a test body that are independent of the mass of the test body, and the forces are indistinguishable from the usual Newtonian gravitational force. The Earth's gravitational field can be counteracted by generating these forces in an upward direction at some spot on the Earth. Forward linearized Einstein's general relativistic field equation and developed a set of dynamic gravitational field relations similar to Maxwell's electromagnetic field relations. The resulting linearized gravitational field relations are a version of Newton's law of gravitation that obeys special relativity. The linearized gravitational field relations show that there is a unique correspondence between the gravitational field and the electric field. For example, the Newtonian gravitational field of an isolated mass is the gravitational analog to the electric field of an isolated electric charge. Likewise, there is an analogy to a magnetic field contained within the linearized gravitational field relations. In Maxwellian electrodynamics, a magnetic field is due to the flow of an electric charge or an electric current. In other words, the electric field surrounding an electric charge in motion will appear as a magnetic field to stationary observers. If the observers move along with the charge, they see no relative motion, and so they will only observe the charge's electric field. Thus, the magnetic field is simply an electric field that is looked at in a moving frame of reference. In an analogous fashion, the linearized gravitational field relations show that if a gravitational mass is set into motion and forms a mass current, then a new type of gravitational field is created that has no source and no sink. This is called the lens tearing effect, or rotational frame dragging effect, in which rotating bodies literally drag spacetime around themselves.